Hello everyone, we'll continue with the next 5 questions of the organic part of September 2022 NET question paper. Right, so we'll be doing only the organic questions. So let's start with question number 6. The question says the major product formed P and Q in this reaction. So you are having a molecule in which we have an alkene part of it, and you are reacting with 9-BBN. 9-BBN is a very bulky boron hydro is a BH3 family member, you can say. It's a bulky group, hydroborating agent, right? And then we are reacting with uh, aldehyde, where the H is changed with a deuterium ion, right? And we want to know what is the P and what is Q. So this is what is 9-BBM. It's a very bulky. It's used for getting stereoselectivity when you do reduction using your boranes. If you use diboron B2H6 or BS3 THF or BS3 diethyl ether, you get less stereoselectivity because they are not very bulky. So to improve the stereoselectivity, we use this 9-BBN. Okay. So now we have this molecule. Now you see this part. This part is coming outside the viewer, this bulky part with the 2-methyl group. And now when this hydroborating agent, especially 9-BBN, we draw it like this for the simplicity's sake. So of course it is too bulky that it will not be able to approach from the front of the screen. It will come from behind the screen because this bulky part is towards the viewer. Okay. So what happens? So once it goes and attacks from away from the viewer, this both hydrogen and this boron group, they goes attacks from behind, and we get species like this. Once you put H2O to OH minus, just it's a rearrangement, and you get OH again from the away from the viewer. So now to better understand, because this question gave like that, so it will be easier for us to just flip this molecule 180 degrees like that. Okay, so I'm flipping it like that. So I'm taking this whole molecule away, so that this CH3 which was top has come down. It was towards the viewer here, so of course it will go away from the viewer here, and H which is away from the viewer comes towards the viewer, and this whole bulky part goes away from the viewer, and you get this. So now when you get this, you can make this structure. So now you can see this boron is towards the viewer, so I am drawing this boron above the plane, and there is a hydrogen which is away from the viewer, which is not seen, so that hydrogen is below the plane. Similarly, this CH3 is away from the viewer, so I am drawing it below the plane, hydrogen towards the plane, and this cyclopropyl I am putting it in above the viewer because this is below the plane. So this part has gone below and this is there. Now what happens is, next step, you are reacting it with your aldehyde. Now aldehyde, what happens? It will undergo what is called as elimination reaction. Now for elimination reaction to occur, we need to form a pi bond. How does a pi bond form? You need two p orbitals parallel to each other. We need two p orbitals parallel to each other, right? So therefore elimination generally happens when they are the leaving group and the proton abstracted is in anti-periplanar, and sometimes when it is in syn periplanar, then also it happens. So here they are in periplanar, so you can see that this sigma bond and this sigma bond, they are in same plane, they are parallel to each other, and therefore this comes away, this comes here, and this goes and attacks here, and you are getting this, right? So this was very interesting case where you have attacked hydrogen on the ketone, so you have reduced it, and then oxygen goes and attacks here because boron is still electrophilic in nature. See, boron has 3 groups attached to its neutral. Its octet is not complete, and therefore basically initially actually lone pair of electrons will attack. So instead of showing in 2 steps, I have shown in 1 step that pi bond is going attacking here. You are getting this. Now when you reduce with H2O2 and NaOH, stereochemistry will be retained. Okay. So what happens? This becomes OH, and you get this. So once you rotate this, because that's how they're given question, so you just put it front 90 degrees, rotate. So what happens? This OH comes front, H goes behind, and because I'm rotating it like this, pulling outside the screen, you please understand this, I'm holding this watch, pulling it outside the screen. So what happens, this pH is going this side, so pH is coming on the plane, D is coming this side, and getting this. The answer is option number B. Okay, I will go slowly, you see, you read through it whatever is written. Oh, I'm so sorry. Yeah. Moving on to the next question, question number 7. The question says the structure of compound A in the following reaction sequence. So you're reacting this molecule with LiBH4 and you're getting A. So we have to find out what is A. And then you are reacting with CF3COH, which is a strong acid catalytic amount. And then you are doing H2O and you are getting this kind of molecule. So we have to understand, first you have to understand what are there in all this. You see here there is a COMe, this is a ester group, this is also an ester group, very bulky, and there is an anhydride group here. Now what we are using is LiBH4. Now LiBH4 is not as reactive as LiLH4 because LiLH4 will reduce even carboxylic acid, but LiBH4 will not. It is like a little elder brother of NaBH4. Now what happens is NaBH4 is a mild reducing agent. It reduces only aldehyde and ketone and does not touch esters stuffs like that. Okay, it will of course NaBH4 will reduce acyl halide, but apart from that it does not reduce anything else, amide, esters or carboxylic acid. But LiBH4 can reduce esters, it can reduce acid anhydride also. Basically what happens is because Li is Li plus, okay, and BH4 minus, BH4 minus. So what do you see here is in NaBH4 and LiBH4 you are having same reducing species, that is BH4 minus, that is BH4 minus. Okay, so why is it reducing agent? Because boron is having negative charge, so all the bonds from boron are nucleophilic in nature, and therefore this pH bond, this sigma BH bond, sigma bonds are rarely nucleophilic, but here because of this negative charge it is nucleophilic, and therefore they reduce by hydride donation, H minus donation, right? So it is same for NaBH4, same for LiBH4. So why the difference? The difference is because it is Li plus. Now Li plus is smaller compared to your Na plus. So Li plus will coordinate with this oxygen lone pair much more strongly. So imagine if Na plus is there. Na plus is much larger in size and therefore positive charge is not so very concentrated. But Li plus is much smaller in size and therefore very concentrated positive charge. So this will rather interact with this rather interacting with that, and therefore oxygen gets positive charge, and therefore this becomes much more electronegative and therefore much more electrophilic in nature, and it reduces. So LiBH4 will reduce even the esters and even the anhydride stuffs like that. So if you think the A is something like it reduces all of them, so it makes this into let me just rub this because it's not very clear. So imagine if LiBH4 reduces this, so this will become alcohol, this will become alcohol, this will also become alcohol, and this will also become alcohol. But can you see anything of such sort here? Nothing is there. So that's why they've given this question. If it was that easy, they will never give. And then what you're seeing is, next step you are seeing that some kind of transesterification happens because lactone formation happens. Lactone, lactone is just a ester which is cyclic form. So very clearly something is happening, that somewhere ester remains like ester, and then some part is becoming alcohol, and that is what is going attacking. That's what is happening, right? So that's the idea. So if you look here, if you look at A, what you're getting here is COOH, and even in C you're getting COH. So clearly whatever happens, this cannot happen because LiBH4 is not H3O plus. It will not hydrolyze esters to carboxylic acid. It will reduce esters to CH2OH. So we can straight away neglect of A and C, right? Now what about B and D? So this looks okay because this can probably reduce this. This also looks okay, it will probably reduce this. Therefore we have to look at the product. This product part, what is seen, you can see that one CH2OH remains free, one OH is attacking. So in all probabilities they will be the right answer, because you're not seeing in the product anything like that, right? So if you see this, yeah, one important thing is what you have to understand is, I just now told you that LiBH4 reduces esters. If it is able to reduce anhydride, it should be able to reduce ester also. But how it is not reducing these two esters? One important thing is, this ester is attached to nitrogen. So what happens is, when it is attached to nitrogen, nitrogen will donate electrons here, and therefore what happens? Where does it donate electron? In the pi anti-bonding molecular orbital of the carbonyl. So it already has extra electrons. So its affinity for H minus, a nucleophile, has reduced. Okay, so they are much less electrophilic. And apart from that, what happens here? This part, tertiary butyl, is very, very bulky. So it will not allow BH4 minus to come close to it, and therefore these two parts don't get reduced, and only this anhydride part gets reduced, and you're getting this, right? Then what happens? This tertiary butyl picks up proton, because you have added trifluorostic acid, and this gets activated. This carbon becomes much more electronegative, and of course then this 6-membered ring will be formed. This goes and attacks, this leaves, and you're getting transesterification. Answer is option D. Okay, I'll go slowly and you please read through it. Please pause it if it is fast. Yeah, moving to the next question. The correct match for the following molecules in column P with the spectral data in column Q is. This was the simplest question in this whole question paper, I guess. So first molecule, ethyl estate. Ethyl estate, is a ester. Then is 2-chloropentane. So it's a alkane. And this one is 1,2-dibromo 2-methyl propane. This is also alkane. And what are the things? Two singlets in proton NMR, H NMR. It's a proton NMR basically. Then second one is peak intensity is at m plus 2 is 3:1 in m is 2. Sorry, I missed this, m is 2. Okay, so m is 2, m is 2, m plus 2 is 3:1 in EIMS. It's basically mass spectrometry. And then third one is absorption spectra at 1740 per centimeter in IR. So one thing is very clear, that this aldehyde, this peak, absorption peak at 1740 cannot be for this and this, because these both are alkanes. Alkanes have only CH stretch. CH stretch does not come out 17. Around 1700, whenever you see, you know it is carbonyl. It will be either aldehyde, ketone, amide, ester, stuffs like that, carboxylic, anhydrides also. So what happens is, basically aldehyde gives absorption peak at around 1725. So aldehyde, C double bond O stretch, C double bond O stretch. So you understand, the stronger the bond, this pi bond is, higher will be the stretch. So when it is aldehyde, it's like this. When you have ketones, imagine if you are having CH3. Now what happens? Now CH3 pumps electron, through hyperconjugation, this CH bond, and this CH bond will overlap with the pi star. So when it overlaps with pi star, this bond becomes weaker because it pumps electron, weakens. So this reduces. So aldehyde comes around 1725 and ketone comes around 1710. If you have amide, let me just draw it for you. If you have amide instead of acid, or instead of aldehyde or ketone, then what happens? When NH2 or NR2 is there, amide, this nitrogen donates electron. So when it donates electrons here, it again weakens this C double bond O bond, because it gets single bond character, and therefore it comes much lower. It comes around 1680, I guess. But when you have esters, okay, whatever I said I have written here, but when you have esters, what happens is, esters oxygen is much electronegative, you see. So its electrons are much happier on oxygen than nitrogen, so it has lower energy, so it's less nucleophilic. For a nucleophile, you need the energy to be much higher, but oxygen has much lower energy. You can see that it is oxygen small, its electrons are closer towards oxygen. It does not donate as happily as nitrogen donate, but it withdraws electrons. Let me rub it and explain to you once again. But oxygen withdraws electrons due to electronegativity, by minus I effect. So when it withdraws electrons by minus I effect, it pulls this pi bond closer towards itself, and therefore this becomes stronger. It comes higher around 1735. So if you are seeing at something at 1740, be sure it has to be ethyl acetate. So I hope everybody knows what is ethyl acetate. Ethyl acetate, aceta, whenever aceta is there, it means CH3 is there next to the functional group. So ester, it is CH3, C double bond O. So that's the acetate part, okay. And then ethyl is your prefix, so it is the substituent on the oxygen. This is your ethyl ester that will come at 1740. Next is, now we have to look between A and B. So if you look here, they said that in the mass spectra you will have, no, not mass spectra, I was saying that in proton NMR you will have 6:1, only 2 peaks will be there, 2 singlets will be there, 3:1, right? Now you can see here, this CH3 is different. In chemical environment, this CH2 is different, this is also different, this is also different, and this is also different. So it should give 4 peaks. It cannot be 2 singlets. So you can just forget that part. So it has to be the mass spectrometry. Now what happens? Chlorine, chlorine, what's the molecular mass? 35.5. Is it possible that what is molecular mass? What is atomic mass? Atomic mass is proton plus neutron. So is it possible that you count proton, neutron, and you will still get some fraction? No. It is because chlorine exists as 2 isotopes. One is chlorine 35 and another one is chlorine 37. Both are in the ratio 3:1. So because of 3:1, and you average them out and you get around 35.5. So therefore you will see that M plus 2 peak is 1/3 of that of M peak, because M peak is 3 times more, and therefore this molecule B will give you mass spec of m is to m plus 2 as 3 is to 1. And this molecule, you can see that on this CH3 and this CH3 are neighboring to a carbon which does not have hydrogen. So of course it will come as singlet. Even this CH2 is next to a carbon which does not have hydrogen, so this will also come as singlet. Now these two are chemically identical, so it will give 6 proton signal, and this will give us 2 proton signal. So 6 is 2 is same as 3 is to 1. Okay, so the answer is option D. What's the answer? Option D. Option D is A is 3. Let me rub it so that it makes more sense. Yeah, you see here, and A is 3, so of course this one comes here. Then B is 2. Yeah, this is here and this one is here, right? I'll go slowly, maybe you can read once again. Question number 9. The following transformation involves, what are the two reactions? That's what they're asking. One is Norris type 2 and second is fragmentation of cyclopropyl diradical on Norris type 1, or Norris type 1 and dipymethane, or Norris type 2 or dipymethane. So first we should know what is Norris type 1, type 2 and dipymethane. So Norris type 1 and type 2 is seen in carbonyl. So if they just break away like that, you get like this, is called as Norris type 1. Okay, alpha cleavage. What is Norris type 2? Norris type 2 is if on the gamma position, see this is carbonyl, so alpha, beta and gamma. If on the gamma carbon has hydrogen, then it undergoes McLafferty kind of rearrangement. So this oxygen picks up this hydrogen, this comes here, and you get a alkene and you get a enol, which will convert into ketone. So this is called as Norris type 2. Dipymethane, what happens? You are having two pi systems which is hindered, like in between two alkenes come one sp3 hybridized carbon, a saturated carbon. So what happens? They first both react and you get 1,4 diradical. You can see here, this is position number 1, this is position number 2, this is position number 3 and position number 4. That's why it is called as dipymethane. So there is 2 pi dipi, in between there is a methyl group, so methane. You get 1,4 radical and then it breaks open, and see here, if this is breaking, you form alkene here and this comes here and forms bond here and you get a cyclopropyl ring here. So now let us look at this question. The question says, of course first one is Norris type 1 because it is breaking up, and then what is happening? This cyclopropyl is opening up, this opens up, this comes here, this comes here, and this carbon monoxide is lost, and this also comes here and this comes here, and you are getting a this system. So this is your answer. So answer is option number B. What's option B? Norris type 1 and fragmentation of cyclopropyl diradical. Okay. Last question for the today's video. The major product in the following reaction is, so you are having this allylic alcohol. Allylic means you have a double bond between, there is a carbon and then next is the functional group with which we are dealing. So because alcohol is allylic alcohol, and you are reacting with titanium isopropoxide, tetraisopropoxide, diethyl tartarate and tertiary butyl peroxide, and second one is red al. this is very famous sharpless epoxidation. Okay, and second one here is a powerful reducing agent, red al. So you're asking what is the product form. So we have to know sharpless epoxidation. Now they have reduced, but previously every year they used to ask sharpless epoxidation. So sharpless epoxidation is important reaction. So what Sharpless, he got Nobel Prize for this. So what Sharpless observed is you can predict the absolute stereochemistry of the product when you are oxidizing, when you are epoxidizing an alkene, which is uh, allylic alcohol with this reagent. So what he said is draw the allylic alcohol in such a way so that the alkene comes in vertical line. So you see this alkene comes vertical line, and this OH should come on the right side. And then he said when you use minus diethyl tartarate, then the attack will occur from front. But if you use plus diethyl tartarate, he got Nobel Prize for it. This was great discovery. And he said that if you use plus diethyl tartarate as catalyst, then epoxidation occurs from behind. So here in this question, because it was minus, so attack occurs from front. So I'm redrawing it. I'm pushing it. See, this O is towards the U. It's coming out of the screen. So I'm just pushing 90 degrees. So when I'm pushing 90 degrees coming in the plane, so this oxygen has attacked from front, you understand? So it has pushed both pH and H behind the screen. Even this H and this part is gone behind the screen, what you're seeing. So when you're pushing it 90 degrees, this OH is coming towards the viewer, this H is coming towards the viewer, and this H and this CH2OH, they still remain behind, but they are coming towards the left side. Now you are reducing. Now Redal is very powerful reducing agent, as good as LiLH4, maybe little less reactive, but very safe. LiLH4 is very explosive, so you have to be very careful while using LiLH4. This one is very safe to use. Okay, so when you use Redal, what happens is aluminum has negative charge, so it coordinates with this oxygen. OH is there, so with the hydrogen, because hydrogen has positive polarity. Once it coordinates, it of course will pump electron on this carbon, because this OH is on this carbon. Now if bonding molecular orbital is here, antibonding has to be here. So when it attacks from here, it will push both hydrogen and this on the top. So that's what is happening. This hydrogen is coming in the plane. I'll just rub and show it more clearly. Okay, so it is attacking in the plane, and what happens, this H goes top, this oxygen also, this carbon also goes top, and you're getting this product. And then what happens, because they wanted the product where CH2OH in the answers given is in the plane, so what we are doing is we are rotating this whole thing. So I am rotating this here so that CH2OH comes in the plane, and then when you rotated this OH has come front, this is away from the viewer, and this pH comes in the plane, you're getting this. That's the answer, is option number C. Okay, I'll go slowly, you can see through it. Okay, that's it for today's class. Thank you so very much.